Dear students, last lecture I already explained what is the meaning of kinetic energy, what is the meaning of potential energy, what is the conservative force, non-conservative force, and after that I already explained work energy theorem in that last video, and after that here I want to explain the another 2 points in this chapter number 2, work and that of energy. First point that I want to concentrate here is law of conservation energy. In 11th or 12th standard in chemistry, in physics also, you learn conservation law of energy, and we know that energy can neither be created nor be destroyed, but it can be converted from one form to the another form. म्हणजे ऊर्जा नाशही पावत नाही आणि उगमही होत नाही, फक्त एका रूपामधून दुसऱ्या रूपामध्ये ती प्रवेश करते किंवा रूपांतरित होते, मात्र टोटल एनर्जी नेहमी कॉन्स्टंट राहते. अशा प्रकारचा जो नियम तुम्ही 11वी किंवा 12वीला त्या ठिकाणी शिकलेला तोच नियम आपल्याला या ठिकाणी डिटेलमध्ये डिस्कस करायचा आहे. फॉर दिस पर्पज we consider one particular body which is at the point A, that means this is the initial state or position of that body, and this body move from point A to B, that is B is final position of that body. Here, conservative force on this force is acting on that body. That means here the total work done does not depend on the path of that motion. That means that body may be travel from A to B along that path number 1, or that body may be travel from A to B from that path number 2. There is work done is same along these 2 paths, and here the motion of this body we can divide into 2 parts, from A to P and that of P to B. And here the work done during this motion from A to B, that is indicated by W A to B, that is given by the particular formula integration from A to P F bar dot dr bar, using the definition of that work done, plus integration from P to B F bar dot dr bar. Say equation number first. Now, as the force is conservative, then here the particular work done integration from P to A F bar dot dr bar is equal to minus U of A. That means total energy at point A, that is equal to that work done from P to A. That means when we consider that particular transition from A to P, F bar dot dr bar, that should be equal to U of A. Say equation number second. These values we write by using the definition of work done. And when that body, that object move from A to P, the work done is given by this equation number second, that is U of A, that is total energy at that point A. And here, when we consider work done from P to B, that is integration from P to B, F bar dot dr bar, that should be given by minus U of B, that is total energy at point B. Say equation number 3. Putting the value of that work done from equation number second and third in equation number first, we have total work done W A to B is given by A to B having the value U of A, P to B having the value U of B. Say equation number 4. Now here A indicates the initial position, B indicates the final position. That means here we can write the total work done W is equal to UI minus UF. UI minus UF, or UF minus UI is equal to minus W. Say equation number 5. That means here the quantity UF minus UI, there is change in energy in a system of particles. UI, that is the initial state which is at which the body is at rest, that means potential energy. When that body is at rest, it possesses only potential energy. But when that body is in motion, that body possesses the kinetic energy. That means potential energy converted into the kinetic energy. And here, obviously, here UF minus UI is equal to minus W. And according to the work energy theorem, we have W is equal to Kf minus Ki. W is equal to Kf minus Ki according to the work energy theorem that we discussed in the last lecture. Then there are two equations for the same quantity. The putting the value of W from equation number 6 in equation number 5, we can write UF minus UI is equal to, with negative sign, Kf minus Ki, where Kf is the kinetic energy at final stage, Ki is the initial kinetic energy at initial position. Therefore, we have UF minus UI is equal to minus kf, minus minus become plus ki. Again, rearranging the terms, here taking this minus kf on this side plus kf is equal to ki, taking this minus ui on that side plus ui. Plus kf, that is potential energy plus kinetic energy at finite position, that is total energy which is known as mechanical energy at finite stage, that is equal to again ki potential energy at initial stage, ui is the potential energy at initial stage, kinetic energy is the ki is the kinetic energy at initial position, that is also total energy which is also known as mechanical energy at initial position. That means from this equation, total energy at finite stage and total energy at initial stage is always equal. That means total energy is always conserved. This is the conservation law of energy or law of conservation energy. That means it indicates that whatever the change in that energy, that means potential energy may be converted into the kinetic energy, kinetic energy may be converted into the potential energy, but total energy is always remains conserved, always remains constant. That means energy can neither be created nor be destroyed, but it can be converted from one form to the another form. This is the conservation law of energy, which indicates that total energy is always remains constant. And after discussing this particular point, here we come to the another point, gravitational potential energy. For this purpose, again we consider a body having the mass m, which is on the earth surface as shown in diagram number 7, figure number 2. Here, this particular body is on the earth surface having the mass m. That means this body and earth as a second body forms a two-body system. Earth we can consider as a one body, and the object that we take into account here as a second body, and this body, these two bodies construct or constitute two-body system. And here, when we want to calculate gravitational potential energy of that body, then to calculate gravitational potential energy, here we lift that body at height h from the ground, earth surface or from the ground, and to lift that body without acceleration, obviously here the work must be done on that body, and this work done is equal to the weight of that body, that is mg, and we know that weight of that body is m into g, mass into gravitational acceleration is always in the downward direction because of that gravity. And when we want to put that body at height h, we must have to apply the force is equal to mg in upward direction, so that that body is lifted in upward direction at height h. That means here work should be done, and this work done during this lifting of that body is given by mg into h. As height increases, work increases. That means here work is directly proportional to the height. Obviously, this particular work done during this lifting of that body with height h is given by mgh. And here this work done is known as gravitational potential energy of that body. That means potential energy is given by mgh. This is the another point from this particular chapter. And after discussing this particular point, I want to take one example. Find work done. Find the work done in moving particle along a vector r bar is equal to 3 I bar minus j bar plus 6k by meter if applied force F bar is equal to I bar plus 3j bar plus 2k bar Newton. That means vector R1 is given in meter, force given in Newton, and by using the definition of work done, F bar is equal to F bar dot R bar. F bar dot R bar. This is the formula to calculate work done. Putting the value of F bar, I bar plus 3K bar plus 2K bar dot with R bar 3I bar minus J bar plus 6K bar. Now here we have to calculate the dot product. In mathematics, you know that there are two types of product. One is known as dot product, another one is known as cross product. And by using the definition of dot product, here we know that I bar dot I bar 1, I bar dot J bar 0, I bar dot K bar 0. Similarly, J bar dot I bar 0, J bar dot J bar 1, J bar dot K bar 0, K bar dot I bar 0, K bar dot J bar 0, K bar dot K bar 1. And using this dot product, which is also known as scalar product, I bar dot I bar, that is 3. Remaining two terms 0 plus 3 J bar dot with minus J bar, that means minus 3. Then 2 K bar dot K bar 1, 2 into 6 plus 12. 3 get cancelled and final answer is 12. And here we know that the unit of work is Joule, 12 Joule. In this way, we can find out the particular work done during that motion of that particle along that vector r1, and by applying the external force F bar, work done can be calculated by using the formula F bar dot r1. Thank you.